Morning, welcome to our very first session of today. I hope everyone enjoyed yesterday's afternoon activities. And yeah, today we have 4 talks in total in the session, and each of those being 25 minutes in total and 5 minutes for the questions afterwards. And yeah, without further ado, I'd like to introduce our first speaker, Wang, who will talk about Taiji, China's space-based gravitational-wave program.
Okay, thank you. Good morning, everyone. My name is Wang, or we can say Wang He in Chinese, and I work mainly on gravitational wave data analysis. And thank you for the invitations. And it's a great honor to speak here on behalf of Taiji community. Today, I will introduce the development paths, current programs, and the future directions of China's space-based gravitational wave program. This is a broad program, and I'm not an expert in every part of it. I will therefore try to present our current programs and understanding as clearly and faithfully as possible. Okay, let me first start with a short history. China began studying space-based gravitational wave detection in 2008, and Taiji was introduced internationally in 2016. In 2019, Taiji 1 was launched as a technology demonstrator and tests several key technologies in orbit. The mission roadmap was published in 2021. Now, the focus is moving forward full mission engineering, system-level tests, data challenges, and science pipelines. So Taiji has moved from the early ideas to in-orbit tests and now toward the mission and science readiness. Yes, Taiji shared many scientific goals with LISA. As we all know, that gravitational wave allows us to study parts of the universe that are difficult to access with light alone. The science can be grouped into 3 broad areas. The first, astro-physics, how massive black holes form and evolve, how complex binaries are distributed in our galaxy, and how black holes interact with their environment. Second, cosmology, using standard science to study cosmic expansion and searching for stochastic signal from the early universe. Third, fundamental physics, testing strong gravity, black hole rain down, and possible deviation from the general relativity. So Taiji is designed to open a broad scientific window in the millihertz band. But what can we actually observe in this window? Okay, the figure shows the millihertz window and compares the expected sensitivities of LISA, Taiji, and Tianqin. In this band, we expect many different kinds of sources. There are galactic complex binaries, massive black hole mergers, the long signals from anomalies, and stellar mass binaries. We may also observe stochastic background from the astrophysical population or the early universe. And of course, there may be sources that we have not yet predicted. So this is a very rich frequency band, and with both known targets and real discovery potential. Okay, now let me briefly introduce the mission concept designed to observe this band. Okay, the full Taiji mission will use 3 drag-free spacecraft in a triangular orbit around the Sun, and laser links between the spacecraft will measure tiny change in distance between the free-falling test masses. Obviously, the overall concept is very similar to LISA. But Taiji has a somewhat longer arm length and a different orbital position. These differences also make future joint observation with LISA especially valuable. But before reaching the full mission, Taiji has followed a step-by-step development path. This slide shows the development path. The first stage was early studies and the mission design. The second stage was Taiji 1, launched 2019, which gave us important in-orbit experience. After that, the focus moved to the key technologies, including drag-free control, laser interferometry, the physimeter, and the gravitational references sensor. Now, the program is moving forward toward the full mission engineer and system integration, verification, and data challenges. So the roadmap has moved from the separate technology test toward the preparation for the full mission. The most important in-orbit step so far was Taiji 1. Okay, here is a Taiji 1, launched in 2019 again as a single satellite technology demonstrator. It tests several key systems in orbit, including LISA interferometry, the gravitational references sensor, microthruster, drag-free control, and the thermal control. The plot on the lower right shows one example. After the drag-free control loop was closed, the modulated disturbance peak was clearly reduced. So, as we all know, well, Taiji 1 was not a full gravitational wave detector, but it gave us a valuable in-orbit experience. It also produced an important science result beyond the technology testing. Using Taiji 1 observations, the team built a global gravity field model called TGGM R1911. The middle figure shows the recovered geoheight anomalies, and the right figure compares the model with the references model, EGM 2008. So Taiji 1 is more than a technology demonstrator. It shows that the platform could support both technology testing and real science. Okay, the next step is to bring the key technology together at the system level. Okay, this slide shows the current engineering focus. There is one mission design tracks and 3 main verification tracks. The first is the overall mission and engineering design. The second is the integration of the core measurement system, including gravitational references sensor, or we can say GRS, and the optical measurement system. The third is a closed loop verification of the drag-free spacecraft dynamics. And the fourth is the full chain verification of the scientific interferometer. On the right, you can see that many key technologies have reached a mature level. Well, some of the end-to-end functions are still being validated. So the main task now is to show that the whole system can work together. Let me first look at the optical measurement chain. Okay, this slide shows the optical measurement chain from the LISA source to link acquisition and pointing control. First, an ultra-stable laser provides a frequency references. Then the interferometer and the physimeter measure the very small phase changes. After that, the acquisition, tracking, and pointing system finds and maintains the laser link between the spacecraft. Finally, the pointing device must be kept under control so that it does not enter the science measurement. And yes, the photo on the right shows the engineering models and the ground test platform. The main point is that they are no longer separate technologies or separate components. They are being developed as the one coupled laser link measurement system. The optical chain measures the motions, so the next step is to keep the test method in free fall and make the spacecraft follow it. Okay, so this is another key part of the measurement system. On the left is the gravitational references sensor, measure the position of the test mass. In the middle, the cold gas microthruster provides a very small and fast forces. And on the right, the drag-free controller uses this information to make the spacecraft follow the test mass. So they are not 3 separate technologies, right? They must work together in one closed loop, sense the test mass, move the spacecraft, and reduce the remaining acceleration. The closed loop system must keep the test mass in free fall, but this also requires the spacecraft itself to be extremely quiet and stable. So this slide shows why the spacecraft itself is a part of the measurement system. First, its own gravity must be controlled near the test mass, and the center of the mass must be placed very accurately. Second, the temperature must remain very stable, because even tiny thermal changes can produce mechanical motion. And third, magnetic, thermal, gravitational, and the structure effect must all be included in the noise budget. So the spacecraft, the payload, and the environment all had to be treated as one measurement system. Okay, the next step is to verify that these parts can work together at the system level. Okay, this slide shows the main system level verification work. First, the payload is being integrated, including the gravitational reference sensor, GRS, optical metrology, laser link, and pointing systems. Second, the drag-free system is being tested in a closed loop with hardware-in-the-loop platforms. Third, the three-arm scientific interferometer is being prepared for full chain verification, including ranging and TDI-related noise suppression. And finally, the end-to-end simulator connects mission dynamics, instrument noise, TDI, and the gravitational-wave signals. You know, the main point is simple. System-level verification is the bridge between the mature component and the emission that is ready to work as a whole. For example, the end-to-end simulator connects the instruction, the data, and the science analysis. Okay, so that leads naturally to the data challenges, right? Okay, this part, you know, in many ways, very similar to LISA. The analysis does not start from the ideal strain data. It starts from raw measurement with clock errors, calibration errors, gaps, non-stationary noise, and many overlapping sources. So the full chain goes from the raw measurement to pre-processing, then to scientific inferences, and finally to science product. Data challenges are very important because they test the whole chain before launch. They also connect the science requirement back to the instrument design. So data analysis is not something added after the mission is built. It is part of the mission design and the validation from the beginning. So Taiji Data Challenge is our main plan for doing this. Yes, Taiji Data Challenge, or we say TDC, is designed as an end-to-end benchmark from the raw measurement to scientific inferences. Compared with the LISA Data Challenge, TDC places more emphasis on full-chain instrument simulation, including laser generation, propagation, interferometry, readout, and TDI. It's also used numerical Taiji orbit on equal arms and multi-source mock data. The data sets and some analysis tools are openly available, so different pipelines can be tested on the same benchmark. The small plot on the lower left shows an example of TDC global field training data. You know, for the more details, please also visit the poster 2.06. So the TDC provides a full benchmark. Now let me briefly show two examples from the pre-processing stage. Okay, because of time, you know, I cannot cover every step in the pre-processing chain, but I only show you two examples. One on the left is the calibration of key GRS parameters, including the center of mass offset and other operation parameters. On the right is TTL coupling. You know, small angular motion can enter the optical path length, so the coupling must be estimated and removed before TDI. This example shows that pre-processing is not just data cleaning, It turns raw measurement into calibrated observables that can be used for the next stage scientific analysis. In other words, after collaboration, the next key step is time delay interferometry, or we say TDI. This is how we turn unequal arm measurements into useful science observables. Right, TDI is needed because the three square arms are unequal and change over time. The raw LISA noise is much larger than the gravitational wave signals, so it cannot be removed by a simple subtraction. TDI combines measurement taken at different times and built a virtual equal arm interferometer. The top figure shows how LISA noise and clock noise are reduced step by step. And the example below shows that TDI is also connected to the glitch propagation, noise categorization, and the size optimized configurations. So TDI is not only the noise cancellation technique. This is a key step that creates the science data, or we can say science observables used by the later analysis. Okay, now the next challenge is trying to separate the many overlaps sources inside them. You know, as we all know, that in the millihertz band, tens of millions of galactic binary overlap and form a strong confusion foreground. There are two ways to reduce it, right? One is the iterative subtraction, find the strongest sources, subtract them, and repeat. The other is a global residual analysis with, for example, RGMCMC, where many sources are fitted together, okay? You know, in both cases, the residual foreground matters because it sets the effective noise flow for the later analysis, for example, MBHB, Emory, and the stochastic background searches. Oh yes, the figures. Yes, the figure also gives a first preview of the gain from a LISA Taiji network, which I will return to later. And there's a poster 2.7 showing another direction, you know, modeling the foreground as a whole, which can help estimate the instrumental noise directly, and reduce the bias in the downstream and MBHB analysis. I will stand in front of that poster afternoon, so feel free to take a look if you're interested. Okay, after foreground reduction, the next challenge is fast and reliable inferences for individual sources. For example, MBHB and Emirates, they all have very different inferences problem. For MBHBs, okay, one of the main goals is a fast posterior estimation while keeping the result accurate enough for rapid follow-up and global phase update. The two figures on the left show normalizing flow result, including both posterior accuracy and collaboration. For Emirates, the main difficulty is the long duration signal and the strongly multimodal likelihood. One option is a staged PSO search over a broad prior range to find the good candidates regions. Another option is, yes, again, flow-based posterior inferences, which can provide a fast starting point for more expensive sampling. And you know, more details are available in poster 5.6 for the Emory flow result. Okay, so the main idea is not one method for every sources. Different sources need different acceleration strategies. For stochastic background, the key challenge is the component separation. The signal is mixed with the astrophysical foreground and instrument noise, so they must be inferred together with a realistic TDI response. Flexible spectrum models are useful when the true background shape is uncertain. So the main message is simple. Reliable SGWB inferences requires joint modeling of the background, the foregrounds, and the instrument noise. Yes, this is still an early step, and the more realistic foreground and noise model remains the future work. Right, the next question, is what we can learn from a population as a whole. This is a preliminary spectrum science study using simulated Taiji Emery population. The main idea is that population mass features can help break the mass relative degeneracy across a catalog, allowing joint inferences of the population model and Hubble constant. So a source catalog can become a tool for cosmology. For example, better distance measurement, larger catalog, and better control of selection effect would make this approach much more powerful. Okay, now, right, from a science-first point of view, the strongest future may come from several missions working together. A network of Taiji, Tianqin, and LISA observe the same source from the different positions and with different antenna patterns. So the gain is not only higher SNR, the different geometries help break the parameter degeneracies and improve the localizations and the distance measurement. The middle figure, yes, the middle figures gives a preliminary MBHB example where the posterior becomes a narrower as the more detectors are added. So yes, the network also provides cross-detector consistency checks, help distinguish and real signal from the detector-specific artifact. So the main network gain comes from SNR, geometry, and consistency together. And more than that, these event level gains then built up at the population level. In the high relative MBHB example, the network detects more light seed events and gives tighter constraint on formation channel fractions. Adding LISA improves them further. So the long-term goal, we'll say, is not only better individual detections, but stronger population, component separation, and even network global field inferences. Again, the strongest long-term science will come from the complementary observatories working together. Okay, let me close with 3 points. First, Taiji is moving from technology heritage toward engineering readiness. Second, data analysis, from simulation and calibration to TDI, data challenges, and global fitting, is being developed as the part of the mission itself. And third, the long-term science case is network facing. We hope to work through common simulations, shared benchmarks, cross-mission analysis, and joint population studies. Yes, the photos. Yes, the photos shows recent coordination between Taiji and Tianqin communities. The two programs are now working toward a joint application for the National Major Science and Technology Program. Yes, this is obviously an important step toward closer coordination in China. So at the same time, we also hope to build an open collaboration with a wider international community. Okay, the final slide with the final image shows that 100-meter triangular laser interferometry test facility now is under construction in Hangzhou. In the photo, you can clearly see that 2 long arms extending away from the central area. And yes, it is a part of the effort toward the full constellation ground verification. Okay, that's all I have. Thank you very much. And I look forward for your question and future collaboration. Thank you.
Okay, thank you for the excellent talk. Do we have questions? Oh, here.
Okay, thanks for the nice talk. I have a curiosity about the implication of your in-orbit test, the Taiji 1. So you measured, because you were in low Earth orbit, 10 to the minus 10 meter per second square per root Earth, right? Of acceleration noise.
Be honest, I'm not quite familiar with that part.
No, I mean, the plots show that, and
okay.
However, we know that we can do sub-femto G we demonstrated, but with another mission in another country. So how you can be confident to be able, when you are in a quieter environment, to feel these 5 orders of magnitudes of acceleration noise that would enable your mission. And I agree, if we can have both at the same time with the same sensitivity about it, would be great. But yeah, I was just curious about the confidence that you have of reaching that and how you build this confidence.
Okay. Be honest, I don't know. I can't answer too much about that because I don't know. So I'm sorry. Yes.
Okay, any other questions? Yeah, Alex?
So thank you for the very nice talk. You rightly emphasized the incredible science that we can do if we have a full network of LISA and Taiji and Tianjin, right?
Yeah.
LISA's data, as we know, will be open with regular data releases. There is unfortunately a political situation that would probably not be conducive to a memorandum of understanding, certainly between NASA and Taiji or Tianjin. What is your plan for data openness, data proprietariness, so that we can actually do this kind of collaboration?
From my perspectives, you know, we're always open to communicate and collaborate, and we also love to share our results and any, I don't know, proper techniques. So, and when you talk about the so-called political issues, to be honest, it's really hard to say too much about that, but I hope in the future this could be much better than the current situation. Yes, that's all I can say.
Thank you.
Yes.
So there's also one question in the back from Jonathan. Oh, online also.
Hi, yeah, we have a question from online. Stefano Vitale asks, do you have a tentative planned launch date for the full observatory?
I mean, when the launch, right? As far as I know, it could be the same with LISA 10 years later. Yeah, that's all.
Yeah, maybe just a short question.
Go there and that's it.
Yeah.
Hi. Can you say a bit more about your plans for the signal content in your data challenges? How complex is the source population currently, and what are your plans for the future?
Okay. Just as what I have said, that we actually, okay, two main points. First, we trying to design it as an end-to-end benchmark, you know, from the raw measurement with hardware simulations or any information from hardware. And so also we also believe that the so-called global fees could be related to the scientific data. I mean the data after the TDI, and also related to the pre-processing part. Okay, the first thing that we really care about, and second thing is that we trying to open all the details about the data generation tools and data challenges. So we're trying to open everything. We want to do that. So, can I answer a question? Okay, thank you.
Okay, maybe another online question? Yeah, okay. Okay, and then we can already... Okay, one more question and then...
Yeah, another online question. Will there be particle detectors and magnetometers aboard the spacecraft?
I'm sorry, can you...
Particle detectors or magnetic field measurements?
I don't know. I'm sorry.
Okay, thank you.
That's far beyond my knowledge.
Okay, then let's thank Wang again for the excellent talk. in the meantime, we can switch the slides. So our next speaker is Luigi Ferraioli from ETH Zurich, and he will talk about LISA GRS sensing and actuation electronics, legacy and perspective for LISA.
Good morning, everyone. Can you hear me?
Yes, we hear you.
Yeah, thanks. I see that you also see my slides, so I can move forward. This morning, I will discuss a little bit about the gravitational reference sensor front-end electronics, how the front-end electronics is impacting on the test mass performances, and what are the legacy from LISA Pathfinder and the perspective for LISA. So we know the mass is, the LISA mass is the core of the instrument. It is supposed to be free floating, and it is providing the reference for the reference mirror for the measurement of gravitational waves. So the purpose of LISA on the arms is to make a mass-to-mass measurement. Distance measurement, but the mass, as I mentioned, is supposed to be free, but free along the main science direction, which is the optical axis, where you see the red of the laser in the right picture here. So on the other degrees of freedom, the mass actually is not free, because there are forces, mainly within the spacecraft, which are perturbing the motion of the mass. And those forces then needs to be balanced by a system, which is the actuation system that the GRS is implementing. And the actuation system is mainly built by electrodes, which are surrounding the mass within the electrode housing. And with those electrodes, we can apply voltages to the mass. And with those voltages, we can steer the motion of the mass. The voltages are applied along the degrees of freedom, which are not the main science here. Unfortunately, I have X and phi he mentioned. There is, in this equation, there is actuation on both degrees of freedom, but in principle, the X-axis, which is always considered as the main science axis, is not actuated. Nevertheless, we have actuation on all the electrodes, because the angular degrees of freedom has to be actuated, and also the other degrees of freedom, y theta and zeta eta, are usually actuated as well. Then there is also the electrodes, which are surrounding the mass, can be also used to sense the position of the mass, the motion of the mass. And this is another function of the gravitational reference sensor front-end electronics. It allows to sense the position of the mass along all degrees of freedom, and so provides a position sensor which is complementary to the optical sensor. How the front-end electronic works, there are the actuation, which is based on audio frequency waveforms in the frequency range between 64 and 272 hertz, which allows to effectively apply a force to the mass, which is a quasi-DC force, or effective DC force on the mass. And you see a little bit the scheme here. There is DFAX, which is commanding voltages, then those voltages are processed by the actuation electronics, and then the voltages then are delivered to the electrodes. On the other side, the same electrodes are used also for sensing, and the sensing is implemented through biasing of the mass with a voltage which is around 100 kilohertz, is 98,304 hertz in LISA as baseline at the moment. And this bias allows to get a sensing measurement, which is effectively an amplitude modulated measurement. So the motion of the mass provides an amplitude modulation on this carrier, 98 kilohertz, and then the carrier is sensed differentially by the transformer, which is in the line of the sensing chain, and then the differential signal is demodulated, and the quasi-DC, which is then the residual motion of the mass, is sensed and digitized and provided to the spacecraft. The sensing position in high resolution mode can provide up to 200 micron resolution and with a nanometer precision. In terms of actuation, we can have nanonewton forces applied with femtonewton precision. Just a little overview of what the sensing was showing on LISA Pathfinder. So in LISA Pathfinder, we had periods in which the test mass was grabbed, so it was not moving. And when it is grabbed, then you isolate the motion of the mass from the performances of the sensing chain, and then you can really measure the performances of the sensing chain. And this is what you see in the pictures here on the right. There is a measurement done in 2 different times when the mass was grabbed. One was February 2016 during commissioning, and one was April 2017 after an event that forced us to grab the mass again. You see that the white noise is more or less the same, but the low frequency noise is different, and this is because the position along Z of the mass was different, and the noise terms, the main noise terms which is contributing a low frequency, is a coupling of the injection voltage noise in the sensing chain through the coupling with the test mass capacitance. So the injection voltage is basically a gain factor, and when the mass is moving and in changing position, then you get a noise which is going up and down at low frequency. The high frequency is mainly dominated by the sensing bridge, thermal noise of the sensing bridge. And then there is also a residual low frequency, which is believed to be residual thermal noise due to the internal component of the electronics of the sensing chain, especially. You see that we also measure the high frequency during the LISA Pathfinder mission duration. It was quite stable, with the exception of April 2017 event that is a little bit unexplained still. But all in all, there was very small drift observed. There is a duality between channels, which is making some channels performing at the limit of the performances expected, and other channels which were above the limit. But this was observed also on ground and was not a problem for the control of the mass. Now we switch to actuation, because actuation is one of the leading terms in the low frequency noise budget of the test mass. You can see here the actuation noise. It's in this region, which is circled by red in the test mass noise budget. And especially around 10 to the minus 4 Hertz, it's providing quite a leading contribution to the noise of the test mass. And the actuation noise, as seen on the right side picture, it is contributed by different effects. And what we know, there is the amplitude stability of the actuation voltages, which are essentially fluctuation of the amplitude that can be both correlated and uncorrelated. Then there is a white noise, which is essentially a down conversion of voltage noise at the frequency of the actuation waveforms, which is happening at test mass. And then there is nonlinearity of the actuators and also actuation crosstalk, all terms mentioned in terms of relevance. So in terms of the main, let's say, the main concept, the main working principle for the actuation, here it is a scheme of the actuation circuit. You can see up left on the screen. The front-end electronics receive the commands from the spacecraft, in which there is a drag-free actuation control system, the DFAX, which is running, getting the position of the mass and calculating what is the voltage to be applied to the mass in order to keep it in place along the degrees of freedom which are actuated. The actuation is implemented, as we mentioned, through the electrodes, which are surrounding the test mass. And there is an entire circuitry within GRS FEE, which is synthesizing the waveforms from the command. We synthesize the waveforms, then we apply those waveforms to the electrodes to an actuation feedback loop, as you see here in the top left figure. What you get at the electrodes, it's not only the commanded voltages, which are basically this, you see the equation here, the commanded voltages are these 1 phi, 2 phi, 1 phi, and 2 phi. You not only get those values, but you get also all the imperfections and the noise which are added by the front-end electronics. And in this imperfection, we mentioned the actuation amplitude stability, both correlated and uncorrelated. Then there are digital errors due to quantization within the electronics, and also nonlinear errors due to nonlinearities in the digital to analog conversion process. Then there is of course, there is also voltage noise, which is in band and also at the actuation frequency. At the end, the force from the voltages can be already calculated to good accuracy with this simplified version of the equations, in which essentially the force is depending quadratically by the voltages that we apply. So now we go one by one through the different contributions to see how they behave and how they impacting the performances of the LISA test mass. Starting from the actuation amplitude stability, because this is the bold guy which is contributing to the noise budget of the test mass. We distinguish between correlated amplitude fluctuation and uncorrelated. The correlated amplitude fluctuation are fluctuation which has a common source to all the electrodes. So all the electrodes feel this common source, and then this contribution is correlated between the different electrodes. Uncorrelated, we mean which are terms of noise which are uncorrelated between the different electrodes. So, and they contribute differently, especially when we consider the LISA case, in which, especially along the x-axis or the main science axis, in this case, we have commands on the phi, but the phi is using the same x electrode. So the electrodes are just 4 on the x phases of the test mass, and the phi is commanded in a way then the voltages, if they are perfect, not affected by noise and imperfection, they cancel each other and you don't have a contribution along x. Nevertheless, the amplitude fluctuation makes a little bit imbalance between the voltages, and this is giving you an effective force also on the x-axis, so also on the science channels, on the science degree of freedom of the LISA. And this is the actuation noise that you see then projected in the noise budget. So how it looks like. In order to show you how big it can look like in LISA, I started I made a simulation using real LISA Pathfinder commands. So I took some commands during a noise run of LISA Pathfinder that was done in February 2017, and then I added amplitude stability fluctuations to those voltages that were commanded at the test mass, and the results is what you see on the screen. The red line is what is our actuation noise requirement. The blue line is what you would have got if you get for LISA the same actuation command along phi that we got on Pathfinder at the time. So it is immediately seen that this contribution is quite dominating the noise budget, especially for the actuation, and there is very little left for the other terms contributing, but it seems that anyway we are safe. This is the leading contribution and the only one that is really dominating the budget. It is important to understand that the actuation, the amplitude stability noise, it is depending at the end, the force noise is depending on the amplitude of the voltage that we are commanding to the mass. The less voltage we command, the less noise we get. And this was the trick that made the LPF, so LISA Pathfinder, so successful. Thanks to an incredibly good balance of the forces on the spacecraft at the level of the test mass, we could lower the actuation voltages to the minimum level, and this lowered also the actuation for noise, the amplitude stability noise, making LISA Pathfinder so well performing at low frequencies. Since it is a voltage-dependent noise, then it was also changing the voltages, the authority of the commanded voltages was the way also to isolate the amplitude stability and to measure the amplitude stability directly in flight. This is what we did on LPF. you can have a look at the paper, which is was published 2 years ago. We commanded different voltage levels to the test mass, increasing the voltage levels from very low to high voltage levels, and this was changing the low frequency noise as shown in the two pictures, high side on the right. This allows to isolate the contributors, and thanks to a model and the fitting procedure based on macro chain Monte Carlo, then the different contribution could be estimated for LISA Pathfinder. And here in the bottom picture, you see what was estimated in terms of contributors. S plus and minus are referring to the electrode on the two sides of the mass. In particular, what is interesting to see also is that what we measured in flight correlate well with what was measured on ground. So this means that on ground, we are able to characterize this effect and this noise to high precision, and this reflects what we will get then in flight. Now, we move towards a different effect, and that was very relevant for LISA Pathfinder, a little bit trickier to understand. But let's try. The actuators, it is receiving commands from the DFACs, and then those commands, it creates a waveforms inside an FPGA. So the waveform is digital at the beginning, and the voltage are applied through a lookup table, and then there is a scaling procedures, and then there is the feedback loop. So the logic in the FPGA was finite, and then there were quantization errors, and those errors were seen in LISA Pathfinder. In particular, here we distinguished between digital error due to lookup table quantization and due to scaling quantization after scaling. So the commands of the voltages that we received, that front-end electronics received from the DFACs, at least on LISA Pathfinder, we're looking like this. You see, the green line is the voltage command, the original voltage command calculated by the DFACs. Then there is a sigma delta loop quantizer, which discretized those commands and send them to the front-end electronics. And the results is the blue line, which is here you cannot see, but there is also the red line, which is the actuator. So the process after all the errors added in the front-end electronics, and you see a little bit difference maybe on the screen between the blue and the red with a little shadow below the red sometimes. This is just the quantization error which is happening inside the front-end electronics. So if you are asking how much this was relevant for LISA Pathfinder, this picture, the spectra here on the bottom gives an example. The green line was with the noise that was measured on LISA Pathfinder before the correction for these quantization errors, and the blue is what you get after the correction of quantization errors. So there was quite a big factor of reduction that was very visible on the LISA Pathfinder data, especially at this low frequency before the 10⁻⁴ Hertz. And those errors are actually relevant and were relevant for LISA Pathfinder because in LISA Pathfinder we have a science observable, this delta G, which included the subtraction of the commanded forces. So you make basically a measure of the displacement of the mass, you calculate the acceleration of the mass, and then you subtract the force that you were commanding. And if the subtraction is done with forces which has an error, then you get your error in your delta G estimation. That was happening because of those digital quantization errors. Bottom left, you see how much those digital quantization errors were, the magnitude of those errors for LISA Pathfinder. They have a sort of an RMS of 10 microvolts over a noise run, which was lasting 1-2 days. Those effect is not very relevant for LISA because for LISA, we don't plan to make this subtraction of commanded forces to the mass, because in principle, we don't command anything to the main science channel, say main science degrees of freedom. Nevertheless, if we end up in a situation in which we have to make a subtraction, then this will be relevant for LISA as well. There is another effect of digitization, which is the scaling. And the scaling is relevant for LISA. So when the waveforms, the digital waveforms are combined together, then the electronics was doing a scaling and another quantization. So now that all the waveform is combined, they are combined also with DC voltages. And if you apply different DC voltages to the electrodes, then you can quantize the voltages to a different level and get a different error. So this means that at the end, the voltages that you get on the opposing electrode, which are supposed to be balanced, they are imbalanced because of this error. And the imbalance, it was small. It was a matter of a few microvolts over an entire, so the RMS was the order of a few microvolts. But nevertheless, this effect is relevant because at the end, it creates an imbalance between voltages, like as an example for electrode 1 and electrode 3, you have the same V1 phi, which is commanded positive and negative, but the digital voltage, the digital error may be different. In this case, then the V electrode 1 and V electrode 3 are not balanced anymore, and it's together with the torque, you get also a force, and this force is a noisy one. And you can see how much is the magnitude with on the picture bottom left. This is really created using 5 voltage command as we got for LISA Pathfinder on February 2017, and calculating this digital error with the model that we have of the electronics. So the calculation the good news is that calculation is very accurate. So we were able for LISA Pathfinder to subtract the effect. But if we don't subtract, what you get on X as a result of imbalanced phi actuation is the blue dotted curves that you see. And that was very relevant in terms of magnitude, because as we compared with our actuation noise requirement for LISA, it is already violating in some regions. So, but this effect actually we were able to remove in LISA Pathfinder, so we were not seeing this contributor anymore. Nevertheless, this could be relevant for LISA, and the plan is to try to avoid at the source this effect, so make an electronics which doesn't include these errors anymore. Then another interesting effect that was recently discovered by the University of Trento, and details are provided in the thesis of Vittorio Chiavegado. There is also nonlinearities in the errors, and those nonlinearities are generated in the feedback loop of the actuation, by the DAC, the digital to analog converter, but especially by the ADC, the analog to digital converter, which is the regulating element of the loop. So those items, if you command a certain voltage, you get error in the digitization. And if you command a certain digital code, you get a voltage which has an error in the conversion. And this is typical of all the DACs and the ADC. It's called integral nonlinearity or differential nonlinearity. And this effect is relevant also for LISA. It is impacting because it is creating an imbalance between voltage, which are supposed to be canceling each other. And when they don't cancel, they create a force. And the contributor to the force is the one that you see in this equation here, delta Fxnl. So from the University of Trento, it was seen that the errors, the difference between the errors between one code element, one code LSB and the other, it's pretty random, and with a certain SNR, which is less than 1 microvolt. But then the error get integrated, and on the long run, when you are spanning more than several number of LSBs, then you get correlation in it, which are relevant or can be relevant. But you see also already on LPF, the plot here on the bottom right, this is how the commanded voltage on phi was looking like. And if you count how many LSB we were spanning along this day, 1 day or 2 of measurement, it is just 9 LSB. So the number of LSB that you jump is very little. This is why then you don't get very much about the correlation within those errors. Now, what I try to do is here is to get the voltages commanded for LPF and try to simulate how big this effect would look like. if you compare to the LISA actuation noise requirement, and this is what you get. It is not a dominating effect. Nevertheless, it may immediately, very soon get big if the errors are a little bit larger than what we have seen, at least what we think that we have seen for LISA Pathfinder. In particular, for this simulation, the voltages, the RMS was close to what was measured at University of Trento, less than or slightly bigger than 1 microvolt RMS. So now let's jump to the perspective for the future for LISA. Here I'm presenting data which are preliminary because the test is still ongoing, but this is the results of the first elegant breadboard for the GRS front-end electronics for LISA. The result of the actuation amplitude stability measured with 1 volt voltage actuation and 7 volt voltage actuations. The measurement is done with a lock-in amplifier and is a differential measurement. So we combine the same voltage to 2 electrodes, then we make the difference, and thanks to this difference, the waveform is subtracted, and we can use a range of the instrument which allows us to get the precision that we need to measure the amplitude stability. Nevertheless, there is also down conversion of the noise, the voltage noise at the actuation frequency because of the mixing with the lock-in, let's say, carrier with lock-in reference, sorry. And this has to be considered also in the measurement. This is good and bad because it's good because it gives you an idea what is the magnitude of the additive noise. The bad because the procedures to disentangle the two contribution is a little bit more cumbersome, and that's why we need at least 2 voltages to make the analysis. Nevertheless, what we can see is that at the moment it looks like that on these channels the voltage, the amplitude stability is below the requirement. We require 45 at 0.1 millihertz, and we get 35 ppm at 0.1 millihertz. So the results are very encouraging, but of course the path to a full flight model is still long. We are still at the breadboard. The engineering model is the next step, and with the engineering model we will have really representative performances of the flight model. The white noise, so the additive noise estimated is of the order of 2 microvolt over square root of hertz, while the requirement is 5 microvolt over square root of hertz. Just to get close to the conclusion, there are a number of talks which are being presented or will be presented today or tomorrow, which are related to the GRS. If you are interested, have a look at that, especially or at the recording or at the talks where they are while they are coming, and to make some conclusion. The architecture of the LISA GRS FEE is inheriting a lot from the LISA Pathfinder IS FEE. Especially the function, the performances are expected to be in line. The actuation amplitude stability is confirmed to be the main contributor to the noise budget for the actuation noise, but this may be saved if the electronics behave fine, and also if we have a very good balance of the forces at the mass level, especially a mass balance around the test mass. The digital waveform synthesis error can be a contributor of noise on X when we actuate on phi, but we plan to remove this source of noise by design with a good design of the digital waveform synthesis algorithm. There is still the nonlinear error, which seems not to be a dominating contributor, but still to be monitored carefully. And the perimeter laboratory tests and show that the breadboard looks like to be on the good track to demonstrate good performances for LISA. And so with this, I conclude my talk. Thank you for your attention.
Okay, thank you very much, Luigi. So do we have a question? Maybe online? So maybe just a quick question from my side. So you showed all of these different levels that can impact the overall error budget. So what do you think, which one is the most troublesome in your mind, and what keeps you up at night? So which of those error budget, the scaling, the non-linearities?
Of course, the amplitude stability, because it's the dominating one. But that one, it's sort of, let's say, known in terms of contributors. We know where the contribution is happening. It's happening mainly on the feedback loop of the actuation, actuation loop. But nevertheless, there are, let's say, measurements looks good, but still there are things to be evolved between the breadboard and the EM, and there are changing also components at component level within the actuation chain, which making the EM measurements a critical step to understand if we are really looking forward to excellent performances for LISA as we see from the breadboard. The nonlinearity as well, it's quite a new entry, and as such makes me a little bit anxious and nervous, as you mentioned. This has to be carefully monitored, and in this case, we see that the nonlinearity are quite big if you span a lot of LSBs. So if the force command or the torque commands are spanning a lot of values, so there is a big drift, then you probably start to suffer from those nonlinearities. If we stay at the level of LPF in which the commands were spanning on days long, very little amounts of different voltage levels, then we probably are still fine, because the actuation chain anyway is very much inheriting a lot of from LISA Pathfinder, and especially the ADC and the DAC are the same components. So we don't expect to get anything which is very much different from what we have seen already on LISA Pathfinder.
Okay, thank you for the additional insights, and let's thank
You're
Luigi
welcome.
again. So our next speaker is Kevin Burdge from MIT, and he will talk about astronomy of ultra-compact binaries.
All right. Well, I've got a lot to say, so I'm going to jump right into it. Let me just plug in. I guess I'll use this clicker. So thanks for inviting me here today, and what I'm excited to get you all hyped up about are ultra-compact binaries, which I think are going to be LISA's premier multi-messenger sources. And so I'm just going to jump right into this, just talking about all of the observables we get out of ultra-compact systems. And I'm going to do that using my very favorite object, which is ZTF J1539. So this is a real double white dwarf that was discovered about 7 or 8 years ago now, with just under a 7-minute orbital period. And I'm just going to use this as a single test case to show you how much information we can extract from one of these multi-messenger sources. So to get into it, this is the LISA Symposium, so I'm going to open with the most obvious of the observables to talk about here, the gravitational waves. So you get this periodic deformation of the space-time metric as the quadrupole moment evolves, as the two things orbit around each other. And it comes with an amplitude that is related to the inclination of the binary, and also this amplitude prefactor that's related to the chirp mass and the gravitational wave frequency, and also the distance. Crucially, these are long-lived sources, and LISA is going to be orbiting around the sun, trailing the Earth, right? And so what it does is it's able to sample the gravitational waves from the source from many different orientations. The source isn't going anywhere, it sticks around. And so you get a pretty nice measurement of the two polarizations. You'll notice they share the same amplitude prefactor, but not the same inclination dependence, and so that actually gets you a pretty nice estimate of the inclination of the binary from the gravitational wave observables. But the real star of the show, in my opinion, are the electromagnetic observables here. So this is not a simulation. This is real data taken with a high-speed imager on a 10-meter class telescope called HyperCam. And you'll notice there's this little star that periodically disappears about every 7 minutes. So what's happening is the intensity of the electromagnetic flux coming from the source is dropping like a rock as one of the white dwarfs passes in front of the other and blocks the light. This measurement of intensity of electromagnetic radiation versus time in astronomy, we call that a light curve. But the real star of the electromagnetic show too is you can take these photons and you can split them up by energy and make a movie out of that. And when you do that, you get something called a spectrum. And in that spectrum, you can see kind of some of these features like these absorption lines and emission lines at certain wavelengths. This is hydrogen. It's telling about the elements in this white dwarf. And you see them move through each other. That's because you've got relativistic Doppler shifts of these two white dwarfs as they orbit around each other. And so these lines are moving by thousands of kilometers per second as they trace the white dwarfs. Of course, you can measure velocities from that and then break out Kepler's laws and do things like measure masses without even thinking about the gravitational waves. It's a highly complementary measurement. And so when I talk about multi-messenger astronomy, I don't mean seeing like a gravitational wave source go off and then after the fact pointing telescopes at the thing to look at the mess of the explosion. I mean looking at all these things at the same time, comparing the phase of the gravitational wave to the electromagnetic waveform, and learning all the things you can when you've got all of these observables to work with. And let me just talk about how much information is encoded in this waveform. So again, this is not simulated data. This is the real deal. So when you look at the gravitational waveform from this, it's a sinusoid, right? It's close to a monochromatic source. Sure, over time you get a bit of a chirp, but there's just not that much information you can encode in a sinusoid. There is a lot of information encoded in this, and let me walk you through how much you can physically read off about the system just by looking at this, just with your intuition. So I've got a little movie to help guide us through this exercise too. The first thing you might notice is you've got this weird sinusoidal wobble outside of the eclipses. What is that? It's actually a day-night cycle on one of the white dwarfs. So this little yellow one is heavily irradiating the other one. And so as you go to its day side, you see more flux. As you look at the cool back night side, it goes lower. Kind of like the new moon is a lot dimmer than the full moon. The night side of the Earth, like nighttime, is a lot darker than daytime, right? That's literally what you're seeing here on one of the white dwarfs in this gravitational wave source. At the peak of that day-night cycle, you get the shallow little secondary eclipse as this white dwarf that's doing the irradiating transits the noon face of the other white dwarf. But the real star of the show is this deep primary eclipse. And let me just walk you through all the things we can read off from it. One is, we know the inclination's close to edge on. You don't get eclipses unless the binary is oriented the right way, right? You can measure it to better than 1/100 of a degree now with the signal-to-noise ratio we have here. The other thing is that eclipse is super deep. And the reason for that is the white dwarf that's being blocked there, the little yellow one, let's call it object number 1, is contributing the lion's share of the electromagnetic luminosity. Why do things contribute more electromagnetic luminosity than other things? Because of sigma t to the 4th. It's hotter, and so it's shining brighter. That's exclusively an electromagnetic observable. You're not going to get temperatures from gravitational waves. You can go a step further and say, whoa, that eclipse really goes to 0. I mean, you saw the movie, right? The thing disappears. And what that means is that hot white dwarf that's contributing more of the luminosity is also being completely blocked, and so you can infer the other white dwarf has to be bigger than it to completely blot it out. So you get radii from it too. Again, exclusively an electromagnetic observable. You can go a step further and say, hey, I know how degenerate Fermi gases work, which is the equation of state for white dwarfs. And I know a small hot white dwarf is more massive than a cool puffy white dwarf. And so you can even say something about the masses just by looking at the light curve. You can go a step further, and if you look at and squint and look at this blue one, you'll notice it's being tidally deformed into a teardrop shape. That's because of the tidal forces from the yellow white dwarf are causing it to start to fill its Roche lobe. The shape of that is determined by the mass ratio of the binary. And so you can even pull that out of modeling the light curve. You might worry, oh, it's being tidally deformed. Could it be leaking matter onto the other white dwarf? Well, the way you check that is you say, if it's accreting, there should be X-ray photons. Some of these things have spectacular X-ray light curves. For this source, you can point big X-ray telescopes like SWIFT and XMM at it, and you see no photons. And you put really good constraints on the possible levels of mass transfer in the system as a result. It also turns out this eclipse is an amazing clock. In fact, it's such a good clock, it was used to calibrate the clock of JWST. That's how good of a timing source this is. And it turns out you can do something really cool with that clock. You can measure how the ticking rate changes over time, the same way that was done for the Hulse-Taylor pulsar and all these other things. And when you do that, what you find is the clock's getting faster and faster and faster because the orbit's decaying, primarily due to the emission of gravitational radiation, though there is more to the story. If it were all just GR, you have this really simple expression between F dot and F and the chirp mass, which I'll note is a really complementary observable to the gravitational wave strain because it has similar dependencies on the chirp mass and the gravitational wave frequency, which lets you pull the distance out of the amplitude if it's just obeying GR. This is the whole standard siren idea. Spoiler alert, though, it's not going to be just GR. One of the ways you could check that with just the eclipse is you could say, hey, I can take a time derivative of that big thing. The 11/3 comes out, I reduce the exponent by 1, and I get this really simple relation between the second derivative, the first derivative, and the frequency with this 11/3 prefactor. You time it long enough and you're going to measure the second derivative and you check, is it 11/3 or not? And then if it's not, it tells you, well, this isn't just GR anymore. This is all just from the eclipse so far, right, in one filter. But if that's not enough, let's keep going. You can look at other wavelengths. So you might say, hey, I want to look at this at like bluer colors. This is about the shortest wavelength you can get from the ground. And you see, oh, that day-night cycle reprocessing stuff is changing. So you're starting to learn about the physics of the reprocessing in the atmosphere of the white dwarf. If you want to go shorter, unfortunately, there's this pesky ozone layer in the way here on Earth. So you got to go up to space with something like Hubble, which can look in the ultraviolet. And what Hubble sees is stunning. That day-night cycle goes away because the reprocessing physics in the cooler secondary is not giving you back any UV flux. It completely down-processes it to much longer wavelengths. That's actually kind of beautiful, though, because I showed you the spectra earlier. When you try to measure the velocities from the ground, you can see these features, but they're these really broad, noisy things that are blended. And it's really hard to measure the motion of the two objects with any reasonable signal to noise because of the blend of the two features. But when Hubble looks at it, all the photons you're getting are just coming from the little yellow white dwarf. You completely get rid of the noise from the other one. And so you get these narrow absorption lines of elements other than just hydrogen in the ultraviolet that let you beautifully trace out the motion of that thing going back and forth. Again, these are real Hubble photons. This is not a simulation. And you get a beautiful velocity measurement. Someone recently asked me, why is there a gap in the data? It gets eclipsed, so you don't get any photons when it's blocked. You guys all saw it disappear. Then you can take the mass ratio you get from the light curve, combined with that, combined with the inclination you have from the light curve, and say, hey, I can measure both masses, and therefore the chirp mass. And therefore, I can make a prediction of what the decay rate should be if this were all just GR, with error bars shown in the shaded region. And I can compare it to the measured decay rate. You might go, Kevin, you forgot the error bars on the measured decay rate. They're there. It's just we've measured it to a part in 10,000, so you can't see it with your eyes. So there is a significant discrepancy here. The thing is shrinking faster than GR, and we've already shown that. You can go further and say, hey, why is it shrinking faster than GR? We think it's because of tides. Well, one of the predictions with tides would be that tides should heat up that cooler white dwarf because they're being dissipated in it. But you gotta measure the temperature of the cooler white dwarf to be able to test any of those models, right? How do you measure its temperature? Well, you need to see photons from it and get an SED. How do you do that? Well, you go to longer wavelengths, and longer wavelengths, and longer wavelengths, desperately trying to get some photons in that eclipse. But this is about the limit of what you can do from the ground. Fortunately, astronomers have this amazing tool for looking at really cool objects. It's this really cool telescope called JWST out at L2 that looks in the infrared and is extremely sensitive. And when JWST looked at this, of course, it calibrated its own clock. But as a bonus, it saw lots of photons down in that eclipse. And so suddenly we had a beautiful measurement of the temperature of this object, which is about 6,000 Kelvin. The best tidal models out there said that this thing should be heated to 15,000 degrees. Sigma T to the fourth, that's a big discrepancy in the amount of energy you're talking about being dissipated. So you're already challenging tidal physics here. You can go further and clean this up and say, hey, this is kind of weird. The optical light curve is like really symmetric around the eclipse, but the JWST data has some kind of a kink in it. Is that a data artifact? It's not. What we actually think is happening is this side of the white dwarf's being heated, like it's its day side, right? Even on planets, we know when one side gets heated, what happens? Their atmospheres try to move some of that heat around to the night side. And so you're literally seeing winds on the surface of one of these objects trying to move that heat around back to the night side. So when I talk about multi-messenger astronomy, like, this is what I mean. Like, it's just absolutely mind-blowing that you can do this much with a source that is a gravitational wave source on top of it, right? LISA's going to give us 10,000 things like this, and they're all different. I told you the story for one. I could talk for another 20 minutes about one with an accretion disk or direct impact, and it would look totally different than the story I just told you. So you might go, well, Kevin, that was cool, but like that was a lot of telescope time to spend on like one source. And sure, there might be some cool tide stuff there, but you haven't really convinced us that it's worth spending quite that many resources on these. Why are they so physically interesting? And so I had a list of like 50 cases, and I decided I couldn't talk about them all, so I'm just going to highlight a couple of them. One of the questions I'm most interested in, I think the broader astronomical community, is like, how do binaries change their orbital periods? And I'm going to talk a little bit at length about how we can use these to probe that. Another really big one that I don't have a ton of time to talk about is like, where do these type 1a supernovae explosions come from that a Nobel Prize was given out because they proved the existence of dark energy, and now we've got a Hubble tension and all of that? In the white dwarf community, yeah, sure, there's consensus that they come from exploding white dwarfs. No one has any idea why the white dwarfs are exploding, like what the progenitors look like. We still don't know why they obey the Phillips relationship and why some don't, and like how we're able to tell the difference. And I actually think LISA has a huge opportunity to make leaps forward in this field with the 1A progenitor problem. And I just want to highlight Emma Chickles, who was at this meeting, discovered a 1A progenitor that is LISA detectable. So we already know that LISA is going to be revealing 1A progenitors. I also just want to say, like, there's a huge diversity of the kinds of white dwarfs that end up in these short orbits. Some of them are really hot, some of them are cool, some of them are made of helium, some of them are made of carbon. And so you also get to study the structure and properties of all of these kind of exotic, near-degenerate or semi-degenerate stars in these systems. You get to do the tides thing. I just mentioned a little bit about that. The thing I want to note, too, that I think is underappreciated is, like, accretion. There are a lot of astrophysicists who study accretion. Like, the entire field of X-ray astronomy was basically built around the phenomenon of accretion, right? Even like the exoplanet community, planet formation is a form of accretion, right? We don't understand it that well still. Part of the problem is our prototype systems for studying it, like X-ray binaries and cataclysmic variables, where you have a star dumping matter onto a black hole or a neutron star or a white dwarf. The reason it's overflowing its rotational and dumping matter is because there's some mechanism of angular momentum loss. Often we like to wave our hands and talk about magnetic braking to explain that, and that causes matter to flow, and accretion disks happen and all of that. The problem is we have to wave our hands about what the angular momentum loss is, and there's no real direct way of measuring magnetic braking in those systems. Well, LISA binaries are amazing, because there we know the mechanism of angular momentum loss, and it's not magnetic braking, it's because they're dumping gravitational waves out, and those are carrying away angular momentum. And we can literally watch them radiate their angular momentum away, so we can measure that directly. And we take away one of the biggest unknowns in X-ray binaries and CVs, in that we're able to just measure the angular momentum loss and go, okay, well, how do the accretion disks behave as a function of different rates of angular momentum loss and donor properties? And I think the thing I'm really excited about is, like, astronomers like seeing pictures of stuff, right? Like, this is why we love the EHT image. Well, with an accretion disk, one of the challenges is we know what binaries look like at edge-on inclinations pretty well, because we can measure their inclinations if they're eclipsing. But I don't think anyone can confidently say this is what an accretion disk looks like at 10-degree inclination versus 30, because no one, if you think you can measure inclinations that reliably face on, you're deluding yourself from electromagnetic observables. But gravitational waves are really good at measuring face-on inclinations. And so suddenly you'll be able to make a map of like, what do accretion disks look like as you're looking down their barrel or at this angle or this angle? And how does the electromagnetic emission vary across these thousands of accreting systems at different inclinations? So I think LISA has a huge opportunity to revolutionize our understanding of the phenomenon of accretion, and that's going to be wide-reaching in its impact. Okay, I'm going to talk about my favorite problem with these, which is thinking about how binaries change their orbital periods. So I mean, when LIGO turned on, one of the first big questions is like, how did these black holes get so big? And like, how are they getting into orbits short enough that they're merging within a Hubble time, right? Because their progenitors don't fit into those orbits. It's the equivalent to the final parsec problem for supermassive black holes. And our hand-wavy way of solving it is, well, there's this thing called common envelope, where a stellar envelope engulfs the compact object. They spiral in, some of the orbital energy goes into expelling the envelope, and out you get a short period binary that GR can now take over and merge it, right? One of the big uncertainties in this whole process is like, how efficiently does that change in orbital energy go into unbinding the envelope? This is often a parameter we call alpha. The problem is to measure alpha, you need to know what the initial orbital period was before the common envelope. You need to know what orbital period it came out of the common envelope and compare that to the binding energy of the envelope. If you look at a pair of merging black holes, you know, okay, it came out of the envelope close enough that this happened within a Hubble time, but you can't really say exactly what period. It could have been 5 minutes or hours or days even, potentially. But the beautiful thing about white dwarfs is they're glowing, but they're not fusing. So if you look at how hot a white dwarf is, you know how old it is, because it's got no fresh energy to put in. It's like a battery that's draining. And so if you know how old it is, you can just run GR backwards and say, okay, well, it's at 5 minutes now and it's this many million years old. It started at 20 minutes. And you know the period it came out of the common envelope. And then you can look at the mass of the white dwarf and like its helium shell and things, and even infer the period before the common envelope. And suddenly you can make these measurements. And people are already using the current double white dwarf, so you have to start to do this with small numbers. And you might go, okay, well, the physics of the common envelope with white dwarf progenitors is going to look different than black holes or whatever, right? But I think the key is we have no class of system where we can even begin to constrain this. And the fact that now we have one is a big deal in just taking some first steps into really understanding the physics of that process. So that's one way you can talk about how binaries change their orbital periods. There was someone earlier who asked about effects on F dots at this meeting and like, oh, are we going to have to worry about like significant non-GR effects in F dots? And I already showed you one example of it. There's another amazing example is, as a binary shrinks, what can happen is, as it's accreting, its donor transitions to a degenerate equation of state. And one of the predictions for modeling is actually it will turn around and start growing in orbit, which if you're used to just GR should sound pretty disturbing, like chirps the other way. That's not fantasy. So Johin Chakraborty, who's here at this meeting, discovered and published 2 of the shortest period AMCVNs, so white dwarfs accreting from other white dwarfs with accretion disks, both under 10 minutes, both nicely in the LISA band. And he did the timing, and one of them had this concave down parabola because the clock's getting faster and it's shrinking. The other one had a concave up parabola because the clock's getting slower. The orbit's growing. So my answer is, are these sort of environmental or non-GR effects a big deal? Well, they can flip the sign. So I would call that not negligible and actually a really rich probe of the exchange of angular momentum due to accretion. There's another really cool way you can use these to study how binaries change their orbital periods. So I kind of crafted this talk based on other things I saw. I noticed a lot of people talking about globular clusters and nuclear star clusters and dynamical interactions. So I just want to note, ultra-compacts and globular clusters and nuclear star clusters are actually a really rich area. And so I was giving a talk like this about a year ago at JPL, and I had been awarded a JWST program to actually look at the 2 densest globular clusters in the Milky Way to try to look for LISA binaries in them, Terzan 5 and LILR 1. I was on a tour of JPL, and we went in the DSN room, and I saw JWST downlinking. It was literally the day it was downlinking my data. And I like raised my hand on the tour and I said, that's my data. Like, can I like go in with a USB drive or something to get it a couple days early? And they're like, no one's ever asked this question on the tour before. So that data came in, it's been spectacular. So these are the two clusters. These are the two densest clusters in the Milky Way, TIR5 and LILR1. Don't look the most impressive because this is an optical image. This is what they would look like, for example, to Rubin. But you look at them with 2 mass, and they just light up like a Christmas tree. And it's because they're behind a bunch of dust near the galactic center. They're in the bulge, and so they're highly obscured in the optical. But you look at them with JWST, and you get beautiful images of them. I was pretty worried we were just going to saturate the whole image, but the angular resolution is remarkable. You stretch the image, though, and the stars are all over the place still. So to give you an idea, you zoom in the little outer corner of the image, the lowest density here, and this is still what it looks like out to the corners. So people saw this and they're like, good luck finding LISA binaries in that. But it turns out JWST, like Roman, are incredible tools because they're in space, so their point spread functions don't change, and they have very stable pointing. And so you can just subtract the images. You don't have to use any fancy algorithm. You can use np.diff. And so I did that, and I made a movie out of it. I don't know if the movie's going to play. Oh, that's a shame. OK, the movie's not working. But what you should see is there are all these little specks that would be coming in and out of the movie. So we found a ton of variable stars all over the place. Even in this tiny little cutout corner, there are like 40 of them. Across the full clusters, there are a bunch. I'll tell you in a moment, including some things that I think may be LISA detectable. So here's a double main sequence star just to show you what the light curves look like. This is crazy to be seeing at 8 kiloparsecs near the galactic center. And you get a huge diversity of waveforms, like this is a white dwarf being eclipsed by a main sequence star. And you get stuff like this. And this could very well be the type of thing that will light up in LISA in the core of that cluster. We need to do further follow-up with JWST spectroscopy to confirm that it's an ultra-compact binary. So just to say, we can access the cores of globular clusters already with things like Webb to look for these objects. And you can study the properties of the binary populations here and say, how different is this from the field? And that teaches you a lot about how do dynamical interactions shape binary populations, even if you're not directly looking at the double black holes in this case. So there are 13 variables known in them. We've got 1,400 of them now. So there's no shortage of binaries to study to see how these environments influence things. OK, so just to say there are a lot of things you can do with sort of the astronomy of ultra-compact binaries to answer, I think, broadly interesting questions. I also saw a lot of talks on the nuclear star cluster. I downloaded some JWST data for the nuclear star cluster and did the same thing. And again, the movies aren't playing, but there are variable stars all over the place. I'll show you some of the light curves. You can tell this is the supermassive black hole because it doesn't look like any of the other light curves, but there's stuff all over the place just within the 10 arc seconds of the galaxy. So I really think like Roman especially is going to crack a lot of this open for us. OK, I'm going to skip over some stuff. I'm going to skip some stuff because I have other things I want to get to, but just to say the time domain surveys have been a big deal in finding them. But what I really want to get to is I showed you a lot of beautiful data, right? I think something that we need to not take for granted within the LISA community is that there aren't many tools that are built to get high-speed movies of millihertz gravitational wave sources. And I say millihertz generally because I'm not just talking about galactic binaries, I'm talking about extragalactic sources too. And so something that I've been working on is trying to build one of these tools at the Magellan Clay Telescope. And we've got these amazing low-noise CMOS cameras that are all over the market now that are like built for our science in particular. And so there's a huge opportunity for our community to build more tools like this. And I'm going to skip over some stuff and just show, this is a light curve I had in my PhD from an old CCD, an EM CCD, state-of-the-art at the time. This is a light curve from a modern CMOS to compare. And so an image I showed last year is we were thinking about trying to build this thing from Magellan to do LISA follow-up. Well, it's actually happened, and so here's a montage of us putting it together in the last year. This is called Lightspeed. Let me just briefly talk about this. So Tyson gave a great talk yesterday about the LISA global fit, right? And the way I like to think about LISA is like, LISA's like a kitchen that cooks a bunch of really nice food. And the global fit is when Tyson, everyone plates that food for us, and we're like ready to go at it, right? And electromagnetic follow-up is when we sit down and take the utensils and eat it, right? But imagine all the food coming from LISA is going to be like really nice soups. And imagine you sit down and all of the observatories, all they have to give you is like, they're like, oh, we only have forks and knives. That's the current state of the situation. And what we're trying to do here, oh, the movie's not playing, of course. What we're trying to do here is build spoons, basically, so that we can actually eat the soup. Sure, you can brute force it maybe with a knife if it's viscous enough, but like it's not going to be a pleasant process, right? And so we've already started publishing a little bit of data with this, but I want to urge the broader community that like it's really important to get this kind of follow-up. These are light curves from big surveys like Atlas and Gaia and Rubin. There's a big difference when you build dedicated follow-up instruments that are low read noise, that are able to kind of sample eclipses at much higher cadences. Rubin takes 30-second exposures. These eclipses don't last that long. And so we really need to get, I think, on building more of these things. And there's a really big opportunity because the US is getting some momentum in getting its ELT going. There are no instruments really suitable for LISA follow-up planned for the European ELT right now. We need big glass for these sources because they're really faint. There's an opportunity here to develop an instrument suite that can actually handle most of the faint LISA sources we have. And just as a final note, I'll just say, like, the reason I say this is broad, you might go, I'm an extragalactic astronomer. Why do I need high-speed imaging? Well, guess what? Sure, if you want to look at the transient aftermath of a merger, sure, you can take a long 30-minute integration. But if you want to see whether your in-spiraling supermassive black hole or whatever is doing anything in the electromagnetic in conjunction with the gravitational waveform as it's merging, you gotta go fast. Millihertz is millihertz, right? By definition, the things are orbiting each other every couple minutes by the nature of how we detect them. And so you can't afford to take 30-minute integrations like supernova astronomers when you're looking at these. And so the same tools that are useful for ultra-compacts are useful for extragalactic science. Okay, so I wanted to end kind of on an interesting note to give something thought-provoking. I hope I've convinced you like the ultra-compacts are pretty exciting. I've kind of been on a crusade for this because when I first started working on them, I was told, oh, these are verification binaries, they're calibration sources, that's why we need them. And it was kind of a bummer. I was like, oh, well, I guess calibration's important. Having worked on them for almost a decade now, I'm like, it's crazy that people thought of these as verification sources. Like, these are so rich. And so here's my take. I think if you polled most of the people in this room today, they'd say that it's the MREs and the massive black holes that are going to define the legacy of LISA. Come find me in 2040 and I will buy you a beverage of your choice based on this bet. My bet is that it's going to be the ultra-compacts that really define our legacy. And not because the MREs and the massive black holes aren't super exciting, but these are setting an incredibly high bar with the amount of astrophysics you can probe with them. And I think that's really going to define like the field of accretion and other things for decades to come. All right, thank you.
Yeah, thank you so much for this interesting talk. I was already a fan of this binary that you introduced initially, but now I'm really excited about this. So maybe one quick question here in the front.
Awesome as always, Kevin. You teased us with that plot showing the tidal impact on the decay, and the models for how the tides impact the orbital decay is something my colleague Hang Yu works on quite a bit and that sort of thing. It sounds like you've got this paper coming out. I'm going to be super interested to see, because I mean, even the people that work on it tell me they don't really trust any of the calculations of what the F dots are from tides. So I don't know. I'm going to be super interested to see how it compares to any of the predictions out there for.
Yeah, it's coming out soon. And like I say, there are two predictions here. There's the decay rate effect, but there's also like, where is the energy going? Like, right. Why is it not heating up the secondary? But yeah, I'll say there have been some surprises, like the outspiraling system too, where we think it's mass transfer. It seems to be going out too fast for us to explain. And so we've even wondered, like, could the accretor have been spun up and actually their tides involve dumping angular momentum back into the orbit from the excessively spun up accretor? So yeah, I think there's going to be a lot of rich physics there. The 7 minutes, a nice clean test case, though, to start with.
I'm going to be looking out for that paper.
Do we have an online question? Okay, then we take another one over here.
Thank you. It's a very good talk. The reason that we love our massive black holes and MREs, where the inspiraler is another black hole, is they keep our beautiful theoretical physics results nice and clean. Do you know of anything like a compact binary with a black hole and a neutron star? Because I imagine with that we wouldn't have to worry as much about things like tides and all the complications, because the black hole is just a black hole and the neutron star is like the stiffest material that can possibly exist. The only thing I know of that's even similar is the nearest black hole that we know of to Earth, which is a wide binary with a main sequence star.
Yeah, and the wide ones are still complicated because you can get things like magnetic braking still kicking in a little bit. But we don't have a black hole neutron star yet. I think one of the holy grails, like the ultimate multi-messenger source for me from LISA, it would be a type of galactic binary, but not a white dwarf one. It would be a system where we find a millisecond pulsar in a gravitational wave source. Like, that'd be the dream, right? Because the timing you can do with the pulsar just blows away anything you could do with the gravitational waveform, and you could like have a blast. What the companion to the millisecond pulsar is, it could be a white dwarf and maybe be a bit messier and teach you about astrophysics. If it were a black hole or another neutron star, then you'd be much more in the GR probing regime. I think either way, everyone should be thrilled if we get a pulsar in a LISA binary. And we may be able to. Those pulsar searches are really hard to do when you're at that short of a period, but the beauty of having a LISA signal is you know the orbital phase and period so well that it just cleans up the pulsar search phase space so much. You even know the inclination well, right? So all these unknowns that normally make compact pulsar searches hard become a lot easier because LISA tells you them.
All right. Let's thank you again. So our next speaker and our last speaker for the session is Krista Lynne Smith from Texas University, and she will talk about X-ray astronomy in the LISA era.
There we go. Okay. So I was asked to give a talk that when I initially received the brief sounded quite challenging, which is X-ray astronomy in the LISA era. And I'll tell you why it's challenging when we get a little further in. I will start by saying that my specialty is supermassive black hole binaries. And I have tried to cover other X-ray applications in this talk, but the organizers did me a solid by putting Kevin's talk right before mine. So you know about the compact binaries. I will talk about them too. Be warned, I taught myself these things about compact binaries during a 12-hour flight delay in the Houston airport lounge. So what you heard from Kevin is probably stronger there. So I want to first explain why X-ray astrophysics is an exceptionally useful and uniquely useful follow-up and precursor observational capability for LISA. And the first is that X-rays can propagate through high column densities, that is, lots of hydrogen atoms between you and the source, and dust particles between you and the source, where UV and optical don't. And that helps you see sources in the galactic plane of the Milky Way when you're looking through the dust in our own galaxy, but it also helps you see sources in distant galaxies that may be dusty because they're inherently young and have lots of star formation, or because they've kicked up a bunch of dust in the merger, or because they're at very high redshifts, where you can have a lot more dusty galaxies than in the local universe. X-rays also are the native electromagnetic product of a lot of these very high energy environments, something that Kevin did a great job of explaining. Yes, indeed, X-ray astronomy grew out of the field of accretion. And so if you're dealing with the native emission from that region, that is easier to interpret than if you are having to work through a lot of the physics of radiative reprocessing, what happens to those X-rays as they move through dust or irradiate surfaces of disks that then re-radiate that emission in the optical or the infrared. And then finally, the variations that you see in the X-rays can happen on extremely fast timescales, and what that's telling you is that you're probing the very smallest spatial scales, sometimes even in very, very large objects, which gives you access to very detailed physics. So I wanted to begin by explaining to maybe folks in the room who aren't so electromagnetically inclined some of the ways that X-rays currently help us inform the phase space of LISA sources. And the first capability is imaging. That's the intuitive one. Of course, we can use imaging in the X-rays here to see 2 AGN in a merging galaxy, and you can't see those nuclei as clearly in the optical and with emission line diagnostics because of the dust. We can search for intermediate mass black hole candidates in galaxies with supermassive black hole candidates. In this image, the little orange squares in the center image are the location of a likely intermediate mass, 10 to the 4 solar mass black hole, close to the purple Seyfert nucleus. And then the cosmological mapping of galaxy clusters in intercluster media. So the hot gas that pervades the centers of galaxy clusters is glowing in the X-rays. And so mapping X-rays can tell us the distribution of the most massive concentrations in the universe, complementary to cosmological surveys in the optical. The next capability is spectroscopy. We can use spectra in the X-rays to measure the black hole spin of supermassive black holes. The shape of certain emission lines is distorted by gravitational redshift as the gas gets closer and closer to the innermost stable circular orbit, or the ISCO. We can use spectra in the X-rays to study abundances in ultra-compact X-ray binaries. And we can also use spectroscopy in the X-rays to see absorption lines from winds that are coming off of the surface of a neutron star after a flare, or another compact object, a white dwarf after a flare. And that kind of wind, the gravitational redshift of those absorption lines in that wind can tell us about the compactness of the binary. And then timing. This is where I do a lot of my own work. There are lots of interesting signatures for LISA sources in the time domain. We can see signals of imminent black hole mergers. There are predictions, for example, in this left panel. You can see that the green line just sort of tanks after the merger has occurred of those 2 black holes with mini-disks. The suggestion is that the X-ray flux would disappear at that stage. There are indications from other work that you might see a jet or an outflow appear after the merger. Extreme mass ratio inspirals, the only electromagnetic counterpart that we have for EMRIs right now, are these very interesting, relatively new discoveries of quasi-periodic eruptions, QPEs, in X-ray light curves. And then, of course, when you have a binary supermassive black hole at a favorable inclination, it can lead to self-lensing flares, these bright flares at a particular phase, at a repeating phase in the sinusoidal variation due to the Doppler emission. So timing is another very important capability for constraining the populations of LISA sources, but also for studying the detailed physics of individual sources. So why was this a challenging assignment? Well, here is what looks like a long and interesting and exciting list of the current X-ray fleet. Now, I'm sorry if your favorite CubeSat or SMEX or something isn't up here. It's got to fit on the slide. But this is a nice, diverse suite of missions with a lot of different capabilities. They're what we have in the sky now. And you can see that they're in order of launch date. And some of these are getting a little long in the tooth, so to speak, but they're still up there, and that's hopeful. So the reason this is a challenging assignment is because I couldn't add any more rows to explain upcoming launches of X-ray observatories, because it isn't clear that there will be more than 1 plus or minus 1 X-ray observatories launched in the next decade or even 2. So there is hope in the fact that many of these missions have lived much longer than their nominal lifetimes. Missions launched in the 1900s, as the students say, are still in flight today. And we have young members of the fleet like XRISM and IXPE that have been launched relatively recently and may last into the future. So the dots mean it's still going. The pluses mean there is a nominal lifetime, but I think it will go longer than that. The question marks mean that something has happened that has stalled or observations in those instruments for now. So there is hope in the lifetimes of these younger missions. But if we stop and we say, okay, we can't plan ahead there's not going to be any X-ray observatories, there's not going to be any X-ray missions moving forward, that kind of pessimism does not put us in the right place to maximize science when an opportunity does show up. So the uncertainty of the opportunities to launch these missions, there is a lot of confusion in the community. There's this Astra call that I'll show you a concept for in a little bit. We need to be ready as a community to jump on mission opportunities when they come into play, and in this fluctuating environment, these opportunities can manifest somewhat unexpectedly. So I'm going to begin the hopeful part by telling you about the capabilities it would be great to have during the LISA era. So the most exciting one, the one you hear a lot about, is follow-up of imminent gravitational wave detected massive black hole mergers. We might see this merger coming days to hours before it actually does occur. And so what we want is to be able to get a space telescope, an X-ray telescope, to quickly respond to the gravitational wave prediction of where that merger might occur as the localization region shrinks. But not only that, ideally, it would be coordinated with ground-based observatories in the optical, infrared, and radio to follow up the detections at the same time as the X-ray mission. Multi-wavelength and multi-messenger have to work together to really constrain all of the detailed physics going on during a massive black hole merger. A key capability, both leading up to the launch of LISA and during the LISA lifetime, is surveying the sky. Not follow-up, we just talked about follow-up. This is a survey, all-sky timing survey. So like LSST is currently just started doing in the optical, we need something like that to be going on in the X-rays, a systematic timing. Now, on short time scales, like hours cadence or to weeks cadence of scanning, we can see those kind of transient signals I discussed where the X-ray emission kind of plummets because of the destruction of those mini disks and catch possible electromagnetic counterparts to merger. This light curve on the right is the tick-tock binary, which is now not a favored binary candidate, but I'm showing it as an example of something that's exciting that we might be able to see, is this oscillation in the periodicity, the period getting shorter. So it's really, really, the idea with this one was the period is getting shorter, it's about to merge. And then it did what AGN do, and it stopped behaving itself, and it just started varying however it wanted. So that was not a binary candidate, but being able to detect those kinds of modulated periods will be key. Multi-wavelength capabilities are very important here. On Monday, I saw two very interesting talks. Scott Noble and Mikhail Chabanov showed indications that outflows from the imminent and pre- and post-merger phases of a massive black hole merger might give rise to, for example, the formation of a radio jet right after the merger that would increase the radio luminosity. So we need to be looking with multiple types of telescopes at the same time. On longer time scales, your survey of months of monthly cadence for many years, that informs us not necessarily about sources that are imminently merging or that will chirp, but that characterizes the source population of massive black hole binaries. So what are the oscillation periods and mass ratios, perhaps even accretion rates of massive black hole populations? So that's survey capabilities, follow-up and survey. The next capability that would be nice is targeted. So let's look at specific sources that aren't necessarily kind of a follow-up to watching the merger happen, but deep characterization of the physics of individual sources. Rapid timing is very important here as well. Photometric timing, that's just getting how bright it is every time you look, but also spectral timing, watching how the spectrum of the source changes with time. And we saw a great example in Kevin's talk of that for a galactic binary. So what this can help you get are period derivatives and orbit characterizations of compact binaries. I'm showing an example here of a candidate black hole white dwarf binary, 47 Tucana X9. You can also get a detailed understanding of quasi-periodic oscillations, which are really nice, very coherent pulsations in the X-ray luminosity of accreting sources. This example is particularly fascinating. It is a tidal disruption event when a star is destroyed by a supermassive black hole and it forms a temporary accretion disk. There's a whole lot of power at a particular frequency in that light curve, a very strong, very coherent periodic oscillation that can tell us the details of accretion flows. And we can understand how the spectral evolution coming from an accretion flow, which changes its geometry based on the accretion rate, will affect the diagnostics that we use to measure mass and spin from the spectrum. Another really new capability in the X-rays is polarization. So we've been studying polarization in the radio for a long time, and in the optical a little bit more recently, but very recently in the X-rays. So one example of many, and this can also be used to characterize winds in compact binaries, in galactic binaries also, is to study the polarization of jets emitted by supermassive black holes. This is a radio study with the Event Horizon Telescope of the jet of OJ287, which is a favorite binary candidate supermassive black hole, watching not the periodicity of the radioluminosity, but the time variation of the polarization swings in the jet. This is a popular science image from IXPE, which is a new X-ray telescope that specifically measures polarization, showing how as the material from the central black hole that gets entrained in the jet propagates up the jet and hits these standing shocks, it becomes polarized and flares first in the X-ray, but then in the visible and infrared light. So again, a multi-wavelength application. Polarization also helps us study magnetic field configurations due to the alignment of dust grains in the vicinity. This is a simulation image of how the magnetic field looks different before on the left and after the mini-disk merger in a supermassive black hole binary, just to give you an example of how magnetic field geometries that we could measure with next generation polarization instruments might tell us something about the detailed accretion physics in a massive merger. So what are the prospects? I said we have to be able to jump on these opportunities, and people are ready to do this. The one on the most solid footing is New Athena. It's an ESA-led mission with a possible launch in 2037, which would be right after the LISA launch and while LISA is in science operations. 12-hour slew times for 1/3 of the sky with 2 instruments, a high spectral resolution imager and a wide field imager also that can see black hole mergers out to about a redshift of 2. Some of the things it can do, the magnetohydrodynamics of gas flows in variable spacetime, as that merger is progressing, what's happening with the X-ray spectrum, what's happening with the accretion disk and the absorbers and the outflows, the formation of jets and coronae in AGN, and as we just saw in Kevin's talk, the relative strength between gravitational wave and matter-driven torques in interacting white dwarf systems. Another concept is axis. This has been not selected for the probe class call in NASA this year, but is being rethought for the Astra initiative, which is a new, mysterious to some of us, still taking shape, call for mission concepts, which initially took the form of a Google form, but is now more reassuringly has a draft in Google Docs. So we're moving up. So axis is being reformulated as either fast or deep axis, probe class proposal with a single instrument telescope. Here are just some examples of how its angular resolution compares to Chandra, which is the one from the 1900s that has a very good resolution, but it gets worse as you get kind of off axis of the main telescope, and some comparisons of its sensitivity to other X-ray missions. And then finally, just to complete the potpourri in your mind of what people are thinking about in terms of next generation X-ray missions, Deus Ex is another Astra concept, which has a fleet of spacecraft. In this drawing, there are 6, and the other one is on the other side of the planet, in a fleet that enables sub-hour follow-up. So very rapid, very steerable follow-up of gravitational wave or other multi-messenger triggers. It does have a polarization capability, and we're integrating some of the heritage technology from CERN and ALICE detectors to handle that. The nuclear astrophysics neutron star equation of state people are liking this one. The timing capabilities are good for them. And it has soft and hard spectral timing as well. So these 3 are not at all the front runners or the most prominent of the Astra concepts or the new ideas, but they give you a sort of a taste of the variety of the different missions that people are still developing the concepts for to be ready for these opportunities. So X-rays are a unique window into the highest energy and the smallest scale processes in the universe. They can see through the dust, they can help us with galactic sources, and they can help us with high redshift extragalactic sources, obscured sources and mergers, that sort of thing. Time domain X-ray surveys are a key discovery space for electromagnetic counterparts to both continuous wave sources, the characterization of the population of massive black hole sources, and merging binaries that are kind of imminent. Rapid timing in spectroscopic monitoring also provides constraints on the actual physics and evolutionary pathways of galactic binaries, the mass ratios, the growth mechanisms for both massive and stellar mass binaries. And finally, the X-ray capabilities during LISA's lifetime, we need a couple of things here. We need long but precedented missions of the current fleet. So we need to hope that what we have up right now can last until LISA's launch. It is a long time from now, but there are missions that have lasted longer. Many missions that have lasted longer. And we also need successful selection of accelerated probe, mid-X, SMEX scale missions when and if those opportunities arise. We need to be prepared as a community to leverage them. And that means thinking a lot about what kind of capabilities will maximize the science that we can do with gravitational wave observatories. So thank you very much.
Thank you for the excellent talk. Do we have questions? Shane?
Thank you, Krista, Lynne. As the science organizing chair, thank you for taking on the task. So I have the following question, especially given the uncertain future of the fleet. Can you comment on the opportunities, whether or not it's worthwhile for spending a lot of time delving into the archives from those missions from the 1900s, looking at archival data to motivate science cases, find LISA counterparts, precursors, whatever?
Yes, as theory becomes better at predicting these multi-messenger signatures and time domain signatures, we have had big changes in what we might expect to see from both merger precursors and post-merger remnants, for example, in the morphology of galaxies and things like that. So the archive stays the same, but our expectations from theory continue to get better. So any kind of support for investigations that go back and mine the archives based on new theoretical predictions are huge. And it's quite possible that combining those with current, the between now and LISA epochs like LSST, I mean, we can make light curves going back to, the 80s that get sufficiently better and better as we add more. The more cycles we get, the better it is. So copy and pasting information, time domain information before to Rubin, to Roman is also a key capability for looking for these sorts of things. So definitely leveraging the archives is a huge, huge plus.
Okay, any other questions? Tyson, yeah?
good to see all the enthusiasm from the X-ray community about Astra, but Astra's focusing really on probe and up.
That's right.
If you were to put the blinders on and say, I just want to pick my favorite LISA X-ray complementary observation case and don't care about anything else, could you shoehorn something into something like a SMEX or a MIDX?
Yes, I will speak only for myself, but for me it would be something NICER-like. So NICER unfortunately lost its pointing capabilities recently, but something with rapid spectral timing I think would be any kind of X-ray timing. I would focus on timing and not on imaging. Spectral timing would be great with NICER. We were just getting some of the most exciting information about the location of the corona and its relationship to the accretion disk. For massive black hole populations, an X-ray timing survey that just scanned the sky photometrically with no spectroscopic capabilities would be a super important way of covering the expected theoretical signatures of massive black holes, especially X-ray periodicities and X-ray self-lensing flares that we don't have and don't really have a prospect of having in the lead up to LISA.
All right. Yeah, there's another question.
Yes, so thank you for this very nice talk. Talking about the X-ray capabilities, there will be, during the LISA lifetime, we hope that there will be new Athena, right? Yeah. That hopefully will be adopted soon, maybe next year. So New Athena has some of the capabilities that you described, like the survey capabilities of the sky, but it will also offer the community this very high resolution spectroscopy in X-rays. So I wanted to ask how this new capability could help LISA science, if you thought about it before.
Yeah, so New Athena is definitely the most concrete thing we have. We hope very sincerely for adoption because it is absolutely essential for some of the X-ray follow-up of transients that we're interested in. So the wide field imager, I mean, we can do some capabilities of quickly kind of tiling fields where we are hoping something might be coming because of a gravitational wave prior. I like the slew time. It says 12 hours, but if we can get on it, we can do great stuff with high-resolution spectroscopy during the merger, which I think would be something amazing to see, where is the X-ray emission actually coming from. There's no polarization capabilities for Athena, which is, that would be a stretch goal. But it reaches a little bit short in redshift, kind of the LISA view, but far enough out that we're still seeing mergers at cosmic noon at a time when a lot of important evolutionary pathways are being entered into. So it's not, I'm more on the time domain side, so it's not something I've thought about as deeply, but watching the spectroscopic evolution of binary candidates is, I think it's the best thing we've got to look forward to. Yeah.
Okay, thank you. I think it's time to thank Krista and all of the other speakers again.